Hi everyone, my name is Nieves and I'm an ocean wave scientist working at the Met Office in Exeter, the United Kingdom. And today I will be guiding you through the different notebooks for the Copernicus Marine Wave Norwest Shelf training. This video is going to cover the part 1 of the notebooks. Then there will be a second video covering part 2 where we will learn how to forecast dangerous wave conditions using as diagnostic large and steep waves. So for this part 1, we will simply learn how to do load and visualize some wave data using some libraries that we've provided together with the notebooks. As you can see here, it's called Wave Tools. So yeah, what is Jupyter Lab? This platform we are going to use. This is basically a web-based interactive development environment for Jupyter notebooks, code and data. It supports different types of languages, and for this practical session we are going to use Python 3, which is one of the most commonly used languages for data science. It is a very accessible language and it's available because it has a simplified syntax and is not complicated. Python codes can be easily written and executed much faster than other programming languages. So regarding the notebooks, the main things to mention before we start with the practical sessions is that we have two types of cell, which is Markdown, which is basically text cells like this one, and code cells that are the ones that have a number on the left, as you can see here, code. We will show you also before we start the buttons to navigate through the notebook, which is basically the play button, or that you can sort key using Shift and Enter to execute each cell. Like for example this one, you can just click and it will run for you. And well, if you have any technical problem, just refresh with this button here on the top. The Jupyter Notebooks allows you to have like a more interactive environment. So here you can navigate through the notebook as you wish, because we've created some hyperlinks for you. So here, for example, if we want to go to section 2 of this practical session, we can just click on it and it will take us to the beginning of the code, and then we can just come back to the table of contents. So basically, in this first part of the training, we will go through a very brief introduction of what are the wave products that we have in Copernicus for the Northwest Shelf. Then we will see how to set up our environment. That is the basic step every time you want to run any Python code. And we will show you through 3 different examples. One for analysis and forecast data that are files with hourly temporal resolution. We will also load some reanalysis data, that is 3 hourly temporal resolution, and then we will finally load some reanalysis data, but in this particular case, data that have been downloaded using the CMEMS subsetter instead of the FTP, as it would be in the first 2 cases. So let's get started. Well, as I've briefly mentioned, this notebook will provide you with a very brief idea on how to load and visualize the CMEMS wave data for the Northwest Shelf. The first thing to mention is that all Northwest Shelf wave products have been generated using WaveWatch 3 in version 4.18. And the model products have been provided using a regular grid resolved at 1.5 kilometers. But this has been interpolated from a native grid that is called SMC, and this native grid has variable resolution that is around 3 kilometers for deep waters of more than 40 meters and 1.5 for the coastal waters. This is the domain here. The CMEMS wave products that can be found in the website are two. The first one is wave analysis forecast. Here you have an hyperlink that will take you to the website where you can find all the information about the product and the main documentation documents that are the product user manual and quality information documents. So if you have any question, just probably it'll be in any of these two documents. And yeah, we've also provided some hyperlink of the viewer. Let's wait a little bit, and it will take us to the product. There we go. So, well, let's start with the actual code. The first step is to install a few standard Python libraries. That for this particular case is going to be NumPy, DataTime, and Matplotlib, because we are going to visualize the data, and for that we need what is called pyplot. And as I've briefly mentioned, we will also import our local library for loading the CMEMS wave data. This local library is in here in this directory tree that you have on your left of your screen. You can actually navigate through it as you wish, and for this part one of the notebooks, we will use the functions that have been written in this module of read CMEMS wave. But you can just go through the different functions if you're interested by yourself, and then I can answer all your questions. But yeah, this is the way to load the modules. So let's start importing the standard libraries. Then we are going to set up the path here. Then we will insert the path where the local library is located. That is going to be different in your case and in my case. That it's basically, if we come back to the main directory, that is going to be actually in here. We import this local library. We are going to call it rdwv, just for like easier writing and reading on the code. We are going to set up our local data directory. All the data is in here, in data, obviously. And we are going to set up also our directory for all the plots we are going to generate. That in this case, what we've done is basically in image, you will have 4 different folders that correspond to each of the practical sessions. So let's run our first cell. Here we are printing the root directory. This is, for this case, my root directory. You will have a different one. And then let's start with our sample A. The files used for this example are a total of 8, and these files encompass the storm Aiden, which is one of the latest storms we've had in the Northwest Shelf. These files follow the nomenclature of files when downloaded through the CMEMS FTP, as I've mentioned briefly in the beginning, which follows this name convention, where the last part of the name is going to be the bulletin production date. And this is going to refer that it's hourly and the validity date of that hourly data. So we will need to point the code at files that have been downloaded from CMEMS, obviously. The next section of this code simply sets the data directory where the files have been stored and the analysis cycle time that is associated with this file. This will be obviously the string date here, following the letter B in the file name. So let's start with our first data that is going to be for the 28th of September 2020. At the present, the model cycles once per day, so hour is always set to 0. Just remember that. And then we've provided also with some extra data if you want to try by yourself a different storm. In this other case will be a storm Dennis, that it corresponds to February 16. So here we just simply cycle through the date we want. And using a standard NetCDF tool such as NCDump or loading the data via Xarray, which is like more standard library, will allow you to inspect the contents of the file. Our local library, that is read CMEMS Wave, this one here, as you see, uses NetCDF standard library, but in the second part of this training, I will show you how to use Xarray, so you will have both. And yeah, this library that we've provided you with, it basically gives you a human readable summary of the wave variables in the file and what's the validity times that are available in your files. It also concatenates all the different files if you have different dates for a period of interest. So the next steps in the code allow us to select one of the Norway Shelf Waves files and check its content. So here basically, since we've already said this is the file we're going to use for this date, let's just read it. So here you can see some information about the file. This is the name of the file. This is where the file is located in products data office, in products data, sorry, this is the name. It's going to tell you what is the temporal resolution, that it's hourly, for this analysis forecast file. And then all the different variables and attributes of those variables. So longitude and latitude, time, the forecast period, then significant wave height, then you will have the spectral moments of primary and secondary swells, direction, peak period, mean period, just the normal wave variables that you will find in most of the wave products. And also like the zonal and meridional component of the Stokes drift. It also prints here, excuse me, the different times that we have. So now let's load the data. Each CMEM wave file that we've provided you with comprises 24 hours of data from the 0 time index. So if we are loading data with forecasts running over consecutive days, the loader will loop over this consecutive date and it will concatenate all of them. For this case, for the storm Aidan, we have a possible range from -24, which is the analysis data, up to 120 hours, which is up to 5 days. But here we are going to just analyze from -12 to 36, which will be 1 day and a half in advance. For Storm Dennis, you could only analyze the analysis data, but you can just download and create a much longer forecast window. We've chosen for this example the significant wave height, but you can just try with a different variable name, that in this case is the peak period. And let's just read the data. Here it prints for you what the code is doing. So it's reading the time indices that you said it should read, so minus 12 to 24. And then it's just loading the data and concatenating the time axis. And here it finally gives you the shape of this data. So in this case, we have the shape, it will be like for time 49, and this is the model domain in X and Y. So here you have some exercises. You can just change the variable imported into var. For the peak period, you just have to uncomment in here. So basically we come back up. It's just uncomment this and remove this one and comment this one. But this is some exercise that you can do by yourself. And then you can just update the forecast day field using different leading times and trying to change, instead of analyzing storm aiding, as in this case, you can just use, for example, storm that is all the data is in this folder. So let's continue. The data we've loaded is in a gridded format, obviously, with the shape of 1240 by 958, and you can simply inspect using basic matplotlib functions, as in here. So let's plot, for example, time index 25, which corresponds to 1 a.m. And we can plot the significant wave height just using pcolorMesh function, where you specify your lon, lat variable, and the data. Here it's important in your array that you specify, okay, the time index, and you take all your x and y. Then here we are specifying that we want to plot the color bar with a pyplot color bar. We can put the title for it, and then we can just save the plot. This is as simple as, well, you just give a name for the plot, and then you just use pyplot.savefig function. This is just the name here and some convention in order to get like a nicest plot and the resolution you want to save it with. So let's run this. We wait a bit, and here we have our plot. Then if we go to images, first example, there it is. Here we have our plot. Okay, so let's continue. Let's go through example B. I'll be a little bit faster in this case because it's just like the same steps we've followed for the analysis forecast data, but in this case for reanalysis. Just remember that in reanalysis we have 3 hourly data, but not 1 hourly data. Here we are going to use Storm Xavier as an example, which happened in the 5th of December in 2013. It was a huge storm affecting the North Sea. Name convention is explaining here. Again, this is the data we are in the date we are interested in, and is 3 hourly, as I've mentioned. Okay, so set the year, month, and day for the analysis cycle. 2013, 12, day 5. Let's cycle. And then let's generate our analysis file name and spec the file as we've done in the previous example. This is following the same steps. Where you will here, for example, like get the content of the chosen netcdf file, again, all the variables with the attributes. This is the names and the validity times of the file. Here, as you can see, is not as long as the previous one, because this is just 1 year, 1 day, sorry, and then we will have the shape of 9 for the time in this case, since it's 3 hourly. So again, we want to plot, or well, we want to read first and then plot our significant wave height. Let's run this. Again, we are reading the data. The data is in this location. This is the name of the file we want to read in, and we are loading significant wave height. And again, as you see, this is the shape with the X and Y, or lat and long. So once loaded in, we can work with the hindcast data in this exactly the same way we would have done for the analysis forecasting example A. So in this case, we want to plot time index 7 that corresponds with 9 p.m. So we just run it. We just have to wait a little bit. And as in the previous example A, we are saving our plot. I just put this name, but you can just change it for the one you wish. And we save our plot in the same exact way we did for example A. And this is the plot we've generated. And as I told you, it was a very it was an extreme event affecting the North Sea, and significant wave height in the domain reached up to 14 meters. And again, the image, you just navigate one, there we have our image. You can just change the easily the layout of the plot. You can change the color bar you're using. In this case, we are just using default. And in the part 1 of the practical session, you can just go through all these settings in more detail. Here we have like some exercise that it would be interesting for you if you want to, where you can compute, for example, the Stokes drift. Since we provide the zonal and meridional components of the Stokes drift, you just have to compute the module of it using this expression. And finally, let's go through example C, where we are going to load a file that have been delivered from the CMEMS subsetter. I've provided this example because it just has a different name convention. So just in case you wanted to try and just see that these libraries are going to work with any name you have. So again, the files from CMEMS subsetter come back with a unique name that it's readable again with the read CMEMS wave function here. And exactly as in the example B, we are going to load data for Storm Xavier, but in this case using again, we are going to use again reanalysis data. Sorry for that. So let's start with, we've specified in this case the exact name. We cannot specify only the year, month and day, and then the cycle you want to load, but you have to specify the exact name. and then you get the content as in the previous example A and B, variables with their attributes. And again, let's plot significant wave height because it seems like the most intuitive variable to plot. We read it in the exact same way that we did in the previous two examples. Let's run the cell. Again, this is the location of the file with the name of the file that you've had to specify first. And let's plot now time index 5, for example, instead of 7, that is what we plotted before, which corresponds with 3 p.m. And again, we just plot using pcolor-mes function. We've changed here the color bar, the color map, sorry, and we specify the color bar in this line again. We generate the title in the exact same way, and then we save the plot and show the plot in the notebook. Let's run it. And there we have it, with the different colors. And again, you have an exercise that you can just try to load a different data set extracted from the subsetter that I've also provided you with in the data folder. So I hope this was useful, and I'll see you in part 2, analyzing sea states from deterministic model data. Thanks a lot. Thank you.